In our last lecture, we learned that images can either be real or virtual. A real image is one that we can project onto a screen, while a virtual image is one that we could see but doesn't actually exist. A flat mirror always produces virtual images because there must always be an observer to look at the object whose image is being reflected in a flat mirror. We can't project that image onto a screen. However, if we could create a curved mirror, certain curved mirrors can form real images. An image that can be projected onto a screen, a real image, is formed when a mirror casts that image on the same side of itself that an object that's being imaged exists. A concave mirror, for instance, is one that has a radius of curvature that points towards an object that we are trying to image. A concave mirror you can think about as looking like the opening of a cave to some object whose image we're trying to reproduce. A convex mirror, on the other hand, is one that's curved away from an object that we're going to try to image. Concave mirrors have focal points where light rays that intersect and then bounce off of that mirror's surface all appear to converge, while a convex mirror has a focal point where rays appear to diverge. The focal point for a concave mirror will be located on the same side of that mirror as an object that's being imaged, while the focal point for a convex mirror will be located on the opposite side of the mirror from the object that's to be imaged. For a particular one of these mirrors, say a concave mirror that's curved towards an object that we're trying to image so that it looks like the opening of a cave, can produce images of objects that might be located in different places depending on where our object is relative to the mirror itself. We'll learn that we can use a technique of ray tracing to think about where and what our image will look like. In this ray tracing model, we'll think about lines of electromagnetic radiation that emanate off an object that we're trying to image. We can think about certain lines passing parallel with an optical axis that runs right through the middle of our mirror. These parallel or P-rays intersect with our mirror and then bounce off, reflected through that mirror's focal point. If electromagnetic rays emanating from our object to be imaged are thought to be traveling at a diagonal, moving through the focal point to intersect with our mirror, then these are called F-rays. An F-ray passes through the focal point and is depicted here in blue for our mirror. As an F-ray is reflected from the mirror's surface, it will bounce back and travel parallel to the optical axis right through that mirror's center. Finally, light rays that travel through a point labeled C, the center of curvature, which is given by 2 times the focal length of a mirror, will pass through that central curvature point, hit our mirror, and bounce back along the same trajectory towards where they originated. Using these techniques of ray tracing, which we'll flesh out more in the coming days, we can show that for a concave mirror, an object placed directly at that mirror's focal length will produce no image in that mirror whatsoever, while an object that's located somewhere between the focal length of a mirror and twice that mirror's focal length will produce a real image, something that could be projected onto a screen, albeit that this image will have a drawback in that it's larger than the original object that we were imaging, and it's also inverted, which means that it will be turned upside down from the original object we were trying to image. Finally, if we place an object closer to our concave mirror than its focal length, then what we'll see is a virtual image, enlarged but on the opposite side of the mirror from where our object originated. And by the way, if you're wondering, an object placed further away from a mirror than its center of curvature will produce a real image that's smaller than our original object and is also inverted. For spherical mirrors, like concave and convex, we define their shape in terms of a radius of curvature. This radius of curvature, r, is a positive quantity in the case of concave mirrors. Concave mirrors, ones that look like a cave opening, are defined to have a positive radius of curvature. For convex mirrors, which look just the opposite, they open away from an object to be imaged, r is a negative quantity, and the radius of curvature has a negative value. Since any light rays traveling parallel to the central axis of a curved mirror will bounce off the curves through a focal point of that mirror, we can always use light rays that are parallel to a mirror's central axis to identify just where the focal point of that mirror resides. Any parallel incident rays reflect off of a curved mirror to its focal point. If we apply this same logic to a convex mirror rather than a concave one, we find that incident parallel light rays reflect off of our convex mirror's surface at a particular angle associated with the curvature of that mirror. If we could backtrace that line of reflected light through the mirror itself to a theoretical point behind that mirror's surface, to the point where that line intersects with the central axis of our convex mirror, then at this location, we would find the focal point of our convex mirror. In both cases, the length or distance from the mirror to its focal point is the focal length, given by f, and it's related to the radius of curvature of a mirror by r over 2. The focal length of a convex or a concave mirror is that mirror's radius of curvature over 2, with the added caveat that r is positive for a concave mirror, meaning that its radius of curvature is on the same side as an object to be imaged. As a consequence, the focal length for a concave mirror is also a positive value, and a concave mirror will have a focal point on the same side as an object to be imaged. A positive focal length indicates a converging mirror, one that focuses light rays in front of it through reflection. For a convex mirror, r is negative, since it lies on the side of the mirror opposite the object to be imaged. This gives us a negative focal length, which means the focal point for a convex mirror will always be on the side of that mirror opposite an object that we're imaging. This indicates a diverging mirror that results in light rays spreading out after they reflect off of that mirror's surface, so that images appear to originate from behind the mirror itself. This is what we mean when we refer to a virtual image. We showed with ray tracing just a few slides ago that if an object is placed inside the focal length of a concave mirror, that object will be imaged so that it produces a virtual representation of that object. That image will appear as though it's on the opposite side of the mirror from the original object that we were trying to image itself. and we'll see something that looks like this. If, instead, our object is outside the focal point of our mirror, then we've seen that we can form a real image, not one that appears to be located on the opposite side of the mirror, but rather one that seems to be projected in front of the mirror itself. And this is what we mean by a real image, something that can be projected. A real image will always be inverted as it is reflected from a concave mirror's surface. While concave mirrors can produce real and virtual images alike, a convex mirror can only ever form a virtual image, because a convex mirror will always have a focal point that's located on the opposite side of itself from the object that we're trying to image. By convention, then, any time that a mirror creates a real image, we will say that that image is located a distance away from that mirror in a positive direction, where that positive direction means that we're on the same side as the object that we're imaging. And conversely, a virtual image will always have a distance from our mirror that's a negative value, because a virtual image will always be located opposite the side of our object with respect to our mirror surface. With that, then, we can come up with an equation that relates the distance that an object is, the distance that an image is, and the focal length for any curved mirror. This mirror equation relates an object's positive distance from a mirror's surface to the distance that an image of that object will be from the mirror's surface, to the focal length of our mirror itself. Our object distance is always positive by default and is given the symbol p. I represents the distance to our image from our mirror's surface. If this is a positive value, then our image is located on the same side of the mirror as our object. And if this is a negative value, then our image is located instead on the opposite side of the mirror from that object. Our focal length can be positive or negative. If focal length is positive, then we must have a concave mirror. If focal length is negative, then we must have a convex mirror instead. Mirrors are capable of enlarging or shrinking objects when they produce an image of them. We refer to this as magnification. And we can quantify the degree of magnification, m, a unitless quantity which represents the ratio of the height of an object compared to the height of that object's image. If an object's image has height h prime, and the object itself has height h, then the magnification of that object in a mirror has an absolute value of m that's given as h prime over h, the apparent height of our object in its image, divided by the actual height of our actual object. Another way to determine the absolute magnification of a mirror is to divide the negative value of whatever our image's distance from the mirror is by the value of our object's distance from a mirror. And anytime this value of magnification is negative as a consequence, our image must be inverted, for the only way for us to get a magnification value that is negative, by virtue of us having this negative sign in the equation, is if I is positive. P is always guaranteed to be positive by default. If I is positive, then that means that a mirror has produced an image on the same side of itself as the object that we were trying to image. And any time that this real image is produced, it will appear inverted in its projection. Separately, anytime magnification has a positive value, that means that our image distance must have had a negative value, and it must be a virtual image, one that appears to be located on the opposite side of a mirror from the object that we're imaging. this image will always be produced upright. So let's work some example problems using this mirror equation and our understanding of focal points for concave and convex mirrors. Suppose that we have a convex mirror illustrated here that's trying to image some object represented by this red arrow, and that this mirror itself has a radius of curvature of 15 centimeters. Our object is located 20 centimeters from the mirror along its optical axis. Where is this object's image going to be located? And will it be real or virtual? Well, firstly, without doing any mathematics, we can say that any light rays coming from our object itself are going to bounce off the surface of this mirror. We could trace those reflected rays back down to a common point, one right along that optical axis through the center of our mirror itself. And what we'd find is where this imagined back-traced line intersects that optical axis, we find our focal point. The focal point for any convex mirror will always be located on the opposite side of that mirror from the object that we're trying to image, and therefore it will have a negative value for length. This length is a negative value because it represents a side of our mirror that's opposite the side that's by default guaranteed to be positive, our object's side. So we have a value that's given to us for the distance that our object is from our mirror. This value is what we've called P in earlier equations, and we're told that this is 20 centimeters. We're told that the radius of curvature of our mirror is equal to 15 centimeters. But now that we know that our convex mirror is going to produce virtual images that are located on the opposite side from our object, we know that our radius of curvature is negative because our mirror itself is curved away from the object we're trying to image. Therefore, I'm going to place a negative sign with its value. In so doing, we'll guarantee that we get a negative value for our focal point, which is precisely what we expect from this ray tracing. Our mirror equation tells us that 1 over the focal length for this mirror is equal to 1 over our object's distance plus 1 over our image's distance for this mirror. Separately, we know that the focal length for any curved mirror is equal to its radius of curvature over 2. That means that we could find the focal length of our mirror by dividing r by 2. Negative 15 centimeters divided by 2 is negative 7.5 centimeters. So now we know how far away from our mirror our focal point is on this side, the opposite side from our object. And so we can use that focal length in this equation, our mirror equation, to determine just how far from the mirror our image must be. From this equation, 1 over our focal length of negative 7.5 centimeters is equal to 1 over our object's distance, a positive 20 centimeters, plus 1 over our image's distance. When we solve for 1 over I and then take the multiplicative inverse of the result, we get a value for our image's distance from the mirror of negative 5.45 centimeters. Our image is located 5.45 centimeters from our mirror. The negative sign tells us that our image will be located on the opposite side of the mirror from our object itself. The focal length of this mirror is negative 7.5 centimeters, which means that our object is sitting somewhere right about in here, on the opposite side of our mirror from where our object itself stands. Our image will be upright, and we can prove that if we calculate what its magnification is. the magnification of this image that's been produced on the right side of our convex mirror is equal to the negative distance that that image is from our mirror divided by the distance that our object is from the mirror. In this case, negative 5.45 centimeters divided by 20 centimeters gives us a unitless quantity for our magnification of about 0.27. So we've magnified our object by 0.27 times. It's shrunk. The value of this magnification is positive, which means that our image is upright. This image is located a negative distance from our mirror, which means that our image is produced on the opposite side of it, from our object. Suppose another mirror focuses an object at a distance of 50 centimeters from it into a real image that's located 20 centimeters from the mirror. If a curved mirror is producing a real image, then we can deduce from this information that our mirror itself must be concave. This means that our mirror effectively looks like this, and an object that's placed on the same side of our mirror as its radius of curvature can have an image that's produced that's also on this same side of the mirror. If an image of this object were located, say, right about here, then that would be consistent with a real image, one that's been projected from our mirror's surface. What's the focal length of our mirror if the distance from our mirror to our object, this distance here, is 50 centimeters, indicative of the value p in our mirror equation, and this distance, which is also a positive value, the distance to our image, is 20 centimeters, then what's f? If 1 over our focal length is still equal to 1 over p plus 1 over I, then this equation is just a matter of plugging in and solving. The key to it is recognizing that a real image will be formed on the same side of a mirror as an object to be imaged, which means that our value for I must be positive in this case. When we solve for 1 over f and then take the multiplicative inverse at the end, we get something like 14.3 centimeters. So our distance to our image is just a little bit further than our focal point itself. Our focal point is located some 14.3 centimeters from our mirror. We were able to deduce in this last problem that our mirror must have been concave. So let's calculate the magnification of that image. We'll recognize that our image must be inverted, and so we'll expect an absolute magnification that's negative. And then finally, if our original object were 10 centimeters tall, how tall would our image be? From our previous work, we know an image distance and an object distance, and we know that magnification can be determined from the ratio of negative I to P, which means we divide negative 20 by 50 centimeters. We get a negative value as a result, negative 0.4, which means that not only have we shrunk our image compared to our object's size, but we have changed its orientation compared to our original object. We've flipped it around. So now instead of pointing up, our arrow is pointing down. It's been inverted. Its magnification is 0.4 times, meaning that if the absolute value of magnification is equal to the height of our image divided by the height of our object, and we know that the absolute value of our magnification is 0.4, then the height of our image is going to be equal to 0.4 times 10 centimeters, which gives us 4 centimeters for the height of our image. So if this object is 10 centimeters tall, then its image is a mere 4 centimeters tall and flipped upside down.